Right now, in this exact moment, you are living through the earliest sliver of cosmic history that will ever be possible. Not the middle of the story, not even close to it. The universe is roughly 13.8 billion years old, and yet the last flicker of light in the cosmos won't fade for a length of time so vast that describing it in years stops being useful almost immediately. Everything you have ever known, every star you've looked up at, every planet, every galaxy photographed by every telescope humanity has ever built exists inside a brief bright window near the very beginning of time, a narrow band of light sandwiched between an origin. We're still trying to fully understand, and an ending stretched across timescales that make the age of the universe itself look like a single second on a clock that never stops ticking. This is the story of everything that comes after us, told using the best physics currently available, and I want to be upfront that some of this is settled science, some of it is educated extrapolation grounded in equations we trust, and a small portion of it is genuine speculation at the outer edge of what physicists are willing to defend in a peer-reviewed setting. I'll be clear throughout about which is which, because a story this enormous deserves honesty about its own uncertainty rather than false confidence dressed up as fact. Before we start the clock, it's worth sitting with just how early we actually are. If you compress the entire expected lifespan of the universe from the Big Bang to the final dissolution of the last black hole into a single calendar year, the current moment, this video, your entire life, the complete span of human civilization would fall somewhere in the first few seconds after midnight on January 1st. Everything that has ever happened to humanity is a rounding error at the very start of a story that is, for all practical purposes, just getting underway. If that scale doesn't unsettle you a little, sit with it for a moment longer, because it gets stranger from here, and if you want to see exactly how strange, go ahead and hit subscribe now, because this channel is going to walk through every stage of that story using real astrophysics rather than vague gestures at infinity. Our own story begins far sooner than any of this, with the death of the star that makes every part of our lives possible. In roughly 5 billion years, our sun will begin exhausting the hydrogen fuel in its core, and contrary to how most people picture a dying star quietly fading out, the opposite happens. As the core contracts under its own gravity, the resulting compression generates enormous additional heat, and that heat causes the sun's outer layers to swell dramatically outward. The sun will balloon into a red giant, its surface expanding to potentially engulf Mercury, Venus, and quite possibly Earth itself, depending on exactly how much mass the sun sheds in the process. A detail astronomers are still refining through observation of other stars going through the same transition elsewhere in our galaxy right now, long before that final engulfment, though Earth will already be uninhabitable. Rising solar luminosity will boil away the oceans, halt photosynthesis, and strip the atmosphere within roughly 1 billion years from now, meaning the actual death of our planet as a livable world happens on a much shorter timescale than the sun's eventual transformation into a giant, a sobering distinction that means Earth's habitability clock is ticking far faster than most people assume. After shedding its outer layers into a glowing planetary nebula, briefly one of the most beautiful objects in the galaxy, the sun will leave behind a white dwarf, an incredibly dense stellar remnant, roughly the mass of the sun compressed into a sphere about the size of Earth, slowly radiating away its residual heat into the freezing dark for essentially the rest of time, a quiet ember marking the spot where an entire solar system once thrived. That fate isn't unique to our star. Every star in the observable universe is running the same clock, just at different speeds depending on its mass, and the ending is the same for all of them. Eventually, every star runs out of fuel. This is where the true scale of the future begins to open up, because the era we currently live in, astronomers call it the Stelliferous Era, the age of Starlight, is itself only a temporary phase in the universe's life. Trillions of years from now, long after the last red dwarf star, the slowest burning and most fuel-efficient stars in existence, finally exhausts its hydrogen, no new stars will be forming anywhere in the cosmos. Star formation requires dense clouds of hydrogen gas, and that gas is a finite resource being steadily locked away inside dead stellar remnants and cooling clouds too diffuse to collapse again. One by one, across a time scale measured in the trillions of years, the lights across the universe will simply switch off, and no new ones will replace them, an ending that astrophysicists sometimes describe less as fire and more as a slow, silent dimming. That transition marks the beginning of what's called the Degenerate Era, and the name isn't a judgment. It's a technical description of the physics involved, referring to the exotic, densely packed state of matter found inside dead stellar remnants. Long before individual stars finish fading, entire galaxies themselves will slowly come apart. Over spans of time reaching into the tens of quintillions of years, Repeated gravitational interactions between stars and between entire galaxies as they drift and occasionally collide will gradually eject a significant fraction of stars and stellar remnants out of their home galaxies entirely, flinging them into the deepening void between galactic clusters. What remains behind will fall inward, most of it eventually swallowed by the supermassive black hole anchoring each galaxy's center, growing that central black hole steadily larger while the surrounding galaxy itself effectively dissolves. So the universe won't just go dark uniformly, it will also physically unravel structurally, its galaxies scattering their contents into deep intergalactic space or feeding them into central black holes, well before the more exotic, later stages of this story even begin. The universe will become a graveyard of dead stellar remnants, white dwarfs, neutron stars, and black holes, orbiting through an increasingly cold and empty darkness. Occasionally, by pure chance, some of these remnants will collide, brown dwarfs merging to briefly ignite as new stars, or neutron stars colliding in catastrophic bursts of light bright enough to briefly punctuate the dark, but these events become progressively rarer as matter continues to spread apart and cool, if any conscious life somehow persists into this era. And this is genuinely speculative territory that some theoretical physicists have explored seriously. It would likely need to cluster near the fading glow of a white dwarf, harvesting its last residual heat, since a white dwarf viewed from Earth's former orbit would provide roughly the same faint illumination as a full moon on a clear night. Eventually, even these will fade. A white dwarf that has cooled completely, radiating away every last scrap of residual heat, becomes what's called a black dwarf, an object so cold it no longer emits meaningful light or heat at all, essentially the ash of a star. It's worth noting explicitly that no black dwarfs currently exist anywhere in the universe, because the process of cooling from white dwarf to black dwarf is estimated to take considerably longer than the current age of the universe itself, somewhere on the order of quadrillions of years. If a single sentence in this video should genuinely stop you in your tracks, it's this one, so go ahead and hit that like button, because the strangest chapters of this story haven't even started yet. Deeper into the Degenerate Era, one of the strangest predictions in theoretical physics comes into play: the possible decay of the proton itself. Protons are one of the fundamental building blocks of ordinary matter, present in the nucleus of every atom, including every atom that makes up your body, and for most of the history of physics, they were assumed to be permanently stable, an unquestioned bedrock assumption underlying most of chemistry. Certain grand unified theories in particle physics, frameworks that attempt to merge the fundamental forces of nature into a single unified description, predict otherwise, suggesting that protons might, over an almost incomprehensibly long timescale, spontaneously decay into lighter particles. I want to be honest here rather than overstate the science. Proton decay has never actually been observed. Massive underground detectors, buried deep beneath mountains, specifically to shield them from cosmic ray interference, have spent decades watching enormous tanks of ultra-pure water, specifically hoping to catch a single proton in the act of decaying, and so far, none has ever been recorded, which has allowed physicists to set an extraordinarily long lower limit on how stable protons must be, well beyond 10 to the 34th power years at minimum. If protons genuinely are unstable at some longer timescale, then given enough time, quadrillions upon quadrillions of years, even the cold, dead matter left over from dead stars, every remaining black dwarf, every planet-sized chunk of frozen rock drifting through the void, will simply dissolve into radiation and disappear. If protons turn out to be perfectly stable instead, this particular chapter of the far future may look meaningfully different, and that uncertainty is, honestly, one of the more exciting open questions in modern physics, rather than a settled prediction, one that multiple next-generation detector projects around the world are actively still trying to resolve. Neutron stars deserve their own moment in this story because they occupy a strange middle ground between ordinary dead stars and black holes. Formed when a massive star's core collapses under gravity too violently to settle into a white dwarf, a neutron star packs roughly 1.5 times the mass of our Sun into a sphere only, about 20 kilometers across, so dense that a single teaspoon of its material would weigh roughly 1 billion tons on Earth. Unlike white dwarfs, neutron stars aren't expected to simply cool and fade in the same straightforward way. Many are expected to remain active far longer, some even continuing to emit detectable radiation as pulsars for extraordinarily long stretches of the Degenerate Era, flickering lighthouses scattered through an otherwise darkening universe. When two neutron stars do eventually collide, the results are spectacular even by cosmic standards, briefly outshining an entire galaxy and forging heavy elements like gold and platinum in the process, the same violent mechanism responsible for much of the heavy metal content found in our own solar system today. As matter itself potentially dissolves and the last conventional stellar remnants fade away, the universe transitions into what's often called the black hole era, And this is where the story becomes, in a strange way, genuinely more interesting rather than simply emptier. Black holes are the most durable objects the universe is capable of producing, vastly outlasting every star, planet, and even the more exotic remnants, like neutron stars and black dwarfs. As galaxies continue their slow gravitational dance across unimaginable timescales, entire galactic structures will essentially become supermassive black holes with smaller orbiting black holes around them, merging with each other again and again, across trillions of years, occasionally growing to masses, potentially reaching trillions of times that of our current sun. When two black holes merge, they release detectable ripples in the fabric of space and time itself, gravitational waves first directly detected by human scientists in 2015, a discovery that confirmed a prediction Einstein had made a full century earlier. In principle, if you could somehow survive near enough to witness a black hole merger directly without being destroyed by it, the stretching and compressing of space around you would translate into something startlingly close to an actual physical sound, space itself literally ringing from the impact, a genuinely strange but scientifically real consequence of general relativity. For a long time, physicists assumed black holes were essentially eternal, permanent scars on the fabric of space-time with no mechanism for disappearing. That assumption changed in the 1970s, when theoretical work demonstrated that black holes aren't actually immortal after all. According to quantum mechanics, empty space is never truly empty. It constantly generates pairs of virtual particles and antiparticles that flicker into existence, briefly separate, and then collide and annihilate each other almost instantly. Near the boundary of a black hole, its event horizon, something unusual can happen to this process. Occasionally, one particle from a pair falls into the black hole while its partner escapes outward, and because that surviving particle lost its partner to annihilate with, it becomes real, detectable radiation streaming away from the black hole. This phenomenon, now called Hawking radiation, after the physicist who first worked out the theoretical mechanism, means black holes are slowly, almost imperceptibly, losing mass and energy over time, radiating themselves away at a rate that's inversely related to their size. Counterintuitively, this means smaller black holes actually evaporate faster than larger ones, since a smaller event horizon produces a stronger, more concentrated effect. A black hole, roughly the mass of our sun, would take an estimated 10 to the 67th power years to fully evaporate through this process. And the largest supermassive black holes at galactic centers, potentially billions of times more massive than the sun, could take up to 10 to the 100th power years, a number so large it has its own informal name among mathematicians and physicists, a googol. For context, that single number is so vastly larger than the current age of the universe that if you wrote out the age of the universe in years and compared it to this evaporation timescale, the age of the universe would round down to essentially zero on the comparison. But slow is not the same as never, and given enough time, quite literally more time than any other number discussed. So far in this video, every black hole in existence, from the smallest stellar remnant to the largest galactic monster, will eventually evaporate completely, releasing its remaining mass and energy as a final burst of radiation before winking out of existence entirely, an event some physicists have described as the last true explosion the universe will ever produce. If you tried to express how much of the universe's total lifespan is actually hospitable to anything resembling life as we understand it, comparing the length of the current star-filled era against the almost incomprehensible span of time stretching out to the evaporation of the very last black hole, the fraction works out to something in the neighborhood of 1 part in 10 to the power of dozens of zeros. A number so close to zero that on any meaningful cosmic timescale, life as we know it exists for essentially no time at all. We are, in the most literal sense physics can offer, living inside a brief flash of light and warmth wedged between an origin and an almost unimaginably long darkness. Once the last black hole has evaporated, the universe enters its final and longest chapter, sometimes called the Dark Era, an epoch defined by almost nothing at all. No stars, no planets, no black holes, no meaningful structure of any kind. Just a thin, cooling mist of photons and fundamental particles spreading further and further apart as space itself continues expanding, drifting steadily toward a uniform temperature infinitesimally close to absolute zero. And this is where the honest answer to, how does it all end, has recently gotten considerably more interesting, because for years, the leading scientific answer to this question has been remarkably consistent. But that consensus is currently being challenged by some of the most important cosmological data collected in the past 2 years. For most of the 21st century, the driving force behind the universe's ultimate fate has been attributed to dark energy, a mysterious force first inferred in 1998 through observations of distant supernovae that revealed the universe's expansion isn't merely continuing, it's actively accelerating. Dark energy makes up roughly 70% of the total energy content of the universe, and remarkably, physicists still don't know precisely what it is. The leading explanation treats it as a property of space itself, a cosmological constant, meaning that as the universe expands and creates more space, it simultaneously creates more of this repulsive energy, an effect that doesn't dilute the way matter and radiation do as everything spreads apart. Under that model, the standard prediction has long been a scenario nicknamed the Big Freeze, where the accelerating expansion continues indefinitely, dragging galaxies apart faster and faster until, eventually, everything beyond our immediate galactic neighborhood becomes literally unreachable and undetectable, with light from increasingly distant galaxies unable to outrun the expansion of space itself, sealing away most of the observable universe's information forever, well before any of the star death timelines described earlier even take place. Here's the genuinely current twist. In March 2025, and again with strengthened results through 2025 and into 2026, an international collaboration using the dark energy spectroscopic instrument, or DESI, mounted on a telescope in Arizona, released the largest three-dimensional map of the universe ever. Constructed based on data from millions of galaxies and quasars stretching back across 11 billion years of cosmic history. When combined with independent data from other surveys, including studies of the cosmic microwave background and additional supernovas observations, the results hinted at something that would have seemed almost heretical a decade ago. Dark energy might not be constant after all. It may be weakening over cosmic time. Follow-up analyses through the rest of 2025 and into 2026, incorporating additional years of DESI observations alongside independent datasets like the Dark Energy Survey, have continued to strengthen rather than weaken that signal, though the researchers involved are careful, appropriately, not to declare final victory. In physics, a result typically needs to cross a specific statistical threshold, what scientists call 5 sigma confidence, roughly a 1 in 3.5 million chance of being a random fluke, before it graduates from an intriguing hint into an accepted discovery. And as of this recording, the dark energy evolution signal, while growing stronger with each new data release, hasn't yet definitively crossed that final bar. If that finding does eventually hold up under the full weight of scrutiny required, it would mean the cosmological constant, one of the bedrock assumptions of modern cosmology for over 2 decades, isn't actually constant at all, and that dark energy behaves more like a dynamic, evolving field than a fixed property woven permanently into space itself. If true, this doesn't just tweak a footnote in an astronomy textbook. It fundamentally reopens the question of how this entire story ends. And if that surprises you as much as it surprised most of the cosmology community, go ahead and hit subscribe, because very few channels are covering how recent this shift actually is. With that uncertainty on the table, physicists currently entertain several genuinely different endings depending on how dark energy actually behaves over the deep future, and it's worth walking through all of them honestly, rather than picking just one. If dark energy remains essentially constant, the traditional big freeze scenario holds, an eternally expanding, ever colder, ever emptier universe stretching toward the black hole evaporation timeline already described. If dark energy is genuinely weakening, as the newest DESI data increasingly suggests, and its strength continues to decline further, gravity could eventually reassert dominance over cosmic expansion, potentially pulling everything back together in a scenario cosmologists call the Big Crunch, a mirror image of the Big Bang playing out in reverse, though on a timescale still likely stretching tens of billions of years into the future at minimum, and current data doesn't yet clearly favor this outcome over the alternatives. And if dark energy instead strengthens over time rather than weakening, a third, more violent possibility opens up called the Big Rip, in which the repulsive force eventually grows strong enough to overcome not just galactic gravity, but the fundamental forces holding galaxies, then stars, then planets, and ultimately atoms themselves together, tearing the fabric of matter apart from the largest scales down to the smallest in a finite and comparatively sudden finale, rather than an infinite slow fade. Current observational data leans toward the weakening scenario, but honestly and explicitly does not yet rule out any of these 3 possibilities with the level of certainty proper science requires before calling something settled. Beyond even these genuinely evidence-based scenarios sits the most speculative territory in this entire video, and I want to flag clearly that everything in the next few minutes moves well past confirmed physics into the realm of serious but unproven theoretical exploration. Some physicists have seriously proposed that our universe may not be alone at all, that quantum mechanics and certain interpretations of cosmic inflation both leave room for a much larger structure, a multiverse, containing regions with entirely different physical constants, some hospitable to something resembling stars and chemistry, others collapsing or dissolving under rules radically different from our own. This isn't a fringe idea dreamed up for entertainment. Versions of it emerge from serious mathematical work on what's called eternal inflation, the notion that the same process that rapidly expanded our universe in its first fraction of a second may never actually stop everywhere, continuing to spawn new, causally disconnected regions of space indefinitely, each potentially settling into its own distinct set of physical laws as it cools. A related and even more speculative idea, explored seriously by a handful of theoretical physicists working at the edges of quantum gravity, involves whether it might be theoretically possible to generate an entirely new, self-contained universe using an almost inconceivable concentration of energy focused at a single point, a process some researchers have nicknamed a baby universe. The mathematics behind this idea draws on the same physics used to describe the earliest moments of our own universe's inflationary expansion, essentially asking whether that process could, in principle, be triggered again, deliberately rather than only occurring naturally at the birth of a cosmos. If such a mechanism is ever proven physically possible, and that remains a genuinely enormous if, resting on physics we don't yet have the technology or theoretical completeness to test, some physicists have mused about the philosophical implication that any civilization advanced enough to survive into the deep future might, facing the eventual heat death of its home universe, attempt to seed a new one as a kind of ultimate lifeboat, an idea that borders on cosmic mythology as much as physics, but one that emerges naturally from taking these speculative equations completely seriously rather than dismissing them outright. There's a deeper implication buried inside that speculation worth sitting with, even if you treat it as pure thought experiment rather than a genuine prediction. If new universes really could be spawned this way, and if only universes capable of developing intelligent life would ever produce civilizations capable of attempting it, you'd have something that functions almost like evolution operating at the scale of entire universes, successful universes proliferating their own descendants, while universes incapable of supporting life simply end without ever reproducing, their physical constants effectively a genetic dead end. It's an idea some cosmologists describe, only half-jokingly, as cosmological natural selection, first proposed in a more rigorous form decades ago and still debated at the margins of theoretical physics today. None of this changes what the equations we're actually confident in predict for our own universe, but it does offer one of the only speculative threads suggesting an ending isn't necessarily the same thing as true absolute finality, even if proving any of it remains, for now, entirely out of reach. Setting the speculation aside and returning to what current physics does confidently support, the eventual fate of our specific universe, under any of the scenarios not involving an early Big Rip, converges on something remarkably similar. The last remaining structures dissolve, the final black holes evaporate in one last burst of radiation, and matter as we understand it ceases to exist in any organized form. What remains is an almost perfectly uniform sea of extremely low-energy photons and fundamental particles, spread across a universe, expanded to a scale that makes even galactic distances look small by comparison. Everything settling toward the exact same temperature, a state physicists call maximum entropy, or heat death. In that state, no further useful energy differences exist anywhere to drive any kind of process, physical, chemical, or otherwise. No gradient left for anything resembling work. Motion, or change to draw upon. Entropy, the measure of disorder in a system, will have reached its absolute ceiling, unable to increase any further because there's nothing left capable of becoming more disordered. In an almost poetic irony, time itself, as physicists understand it, is fundamentally tied to entropy's ability to increase, the so-called arrow of time, the very reason we experience a past distinct from a future in the first place. In a universe that has reached maximum entropy and can get no more disordered, that arrow effectively stops pointing anywhere at all, leaving a cosmos that isn't just dark and cold, but one in which the very concept of next may cease to have any meaningful definition, forever. It's worth stepping back from these staggering timescales and asking what any of this actually means for anyone living through the universe's brief, bright opening chapter. Every star that has ever burned, every planet that has ever formed, every conscious mind that has ever wondered about any of this exists inside a window of cosmic time so narrow it barely registers as a rounding error against the full span of what's coming. And yet, that narrow window is also the only part of this entire multi-trillion-year story capable of understanding any of it, capable of building telescopes, mapping galaxies 11 billion light-years away, and working out, using nothing but light, mathematics, and patience, roughly how a 15-billion-year-old universe still in its infancy is likely to spend the overwhelming majority of its unfathomably long life. There's something worth genuinely appreciating in that fact, rather than only finding it bleak. A universe this vast, this old, and this destined for eventual silence still managed, in one small corner, during one impossibly brief moment, to produce something capable of turning around and asking how the whole story ends, and then actually working out a defensible answer using nothing but curiosity and mathematics. Whatever conclusion you draw from a story this large, whether it leaves you unsettled, oddly comforted, or simply awed at the scale of it, that reaction is itself only possible because you happen to exist during the one sliver of cosmic time when existing, and wondering about any of this at all is possible in the first place. If this journey through the deepest future physics can currently map gave you a genuinely new sense of scale, make sure you're subscribed, drop a like, and let me know in the comments which stage of this timeline hit you hardest. The death of our own sun, the almost impossibly long wait for a black dwarf to form, the evaporation of the last black hole, or the newest twist in this story, the possibility that dark energy itself might be quietly changing right now, rewriting an ending that cosmologists thought they'd already worked out. This channel will keep tracking exactly what the next generation of dark energy surveys reveals, because for the first time in over 2 decades, the final chapter of the universe is genuinely back up for debate.